This is a quick introduction to materials. I'll be using a lot of Blender and Unreal examples, but this is a topic that's pretty universal to any kind of rendering. It's the way we tell computers how surfaces should look using different kinds of texture maps that I'll explain briefly. The code that we use to make a material or tell the computer how a surface should look is called a shader, which makes sense because what we're really dealing with is light, shade, and shadow. Without light, every surface is going to be black. If I asked you to draw a circle, you would probably make something like this 2D image of a circle. And then if I asked you to make it look 3D and turn it into a sphere, you'd probably add some shading like this crescent shape here to suggest that it has a lit side and a shaded side. And then there's the cast shadow falling onto the floor, but that's not on our sphere. And as long as the sphere is a solid object, that shadow on the other object is really not part of the material on our sphere. And we can see the shapes in a totally white room that's all covered with the same paint because the different planes are angled differently to the light and therefore reflecting different intensities of light into our eyes or into the camera. In other words, the different parts of the wall are shaded at different levels so that we can make out the 3D environment. And then how sharply the light bounces back to us is a result of the roughness of the surface. The rougher the surface, the more light is scattered and diffused. A very smooth surface reflects a lot of the light right back at us and appears glossy. So a little bit of history here. While working on his PhD at the University of Utah, Martin Newell developed the algorithm for hidden surface removal, essential for 3D modeling. And in order to test his math, he needed a model with both a curved and sharp edges, and his wife suggested that he use their teapot. So he painstakingly plotted the points on the teapot and used it to demonstrate the earliest shaders. And the Utah teapot is still a benchmark object, and it has made its way as an Easter egg into dozens of places. And then Jim Blinn developed graphics for NASA and JPL, and he collaborated with Boitong Fong on the Blinn-Fong shader that's still in use today in OpenGL shading. Fong shader is more complicated and calculated specular reflections and was used for glossier surfaces. And Ed Catmull painstakingly measured and modeled his hand while at school to demonstrate smooth surface computer animation. And Catmull would go on to work at Lucasfilm, Industrial Light and Magic, and co-found Pixar. And his math is still used today in things like subdivision surfaces. And these three and Newell were all classmates at Utah at the same time. And unfortunately, Fong sadly died young. Software like Maya still uses Blinn and Fong shaders as a base for materials, and you'll see Catmull's name popping up in places like Blender's subdivision modifier. Now, I don't want to go too much into the math here. I just want you to appreciate that the tools that we will be using almost effortlessly are the result of decades of hardcore math and engineering. And what makes the latest game or Hollywood visual effect look amazing are the improvements to the lighting and the material processing. All right. We'll look at UV maps more in a bit, but just understand that all materials are wrapped around a 3D object like wrapping paper. And you probably know already about X, Y, and Z space, world space. Those are coordinates that let us know where an object is relative to the center of the scene. But U, V, and W space is used to plot the points on the surface of a 3D object. U and V are like width and height on the face, and W is rarely used. Instead, you're far more likely to hear the term normal used to describe the direction perpendicular to the face. Okay, so imagine a little whisker growing straight out of every face on an object, like this little icosphere up here in the corner. That's the normal. The shader is calculating the angle of the light in the scene with the angle of each face to determine how bright that face should be rendered. For example, on this icosphere, one of the faces is pointing directly at the light in the scene. So the normal of that face and the angle of the light are the same. And the next faces over are angled slightly away from the light so the computer shades them a bit more. And then the face at the top of the sphere is still in view of the light, but it's 56 degrees off of the direct angle, so it's going to be darker. And then if you keep on going around the surface, soon you'll get faces that are not pointing at the light at all. Most software has a default ambient light on in the scene to prevent faces from going entirely black, but if you turn off that light, any faces not visible to the light rays will be black. All right, and you can see this again here in this photo of a 20-sided die. Number 18 is the face that's pretty much pointing directly at the light, so it's the brightest face. 2 and 4 are pretty close, but slightly darker as they're slightly angled away from the light. 12 and 20 and 14 are even darker, while 8, 16, and 6 are facing away from the light and get the most shade. And those faces are completely black down here in the 3D model in that photo, as they are completely black with no other light in the scene or no other surfaces to bounce the light back onto it. Now you can see that a lot if you see colored light, the surface that the light is bouncing off of, like in this example of Lincoln's face here. That's got a really strong color, and so the light being reflected back onto his face there is that same orangey pink color. This is called radiosity or color bleed. And the faces in the 3D model are totally black because there's no other light or surface in the scene to reflect onto those dark sides. And you can see this in stage or studio lighting where the subject is lit with a single bright light against a dark background. Okay, all that takes us to PBR, not past blue ribbon, but physically based rendering. The metal PBR workflow is by far the most common shader model used in realistic rendering. Basically, it's using 3 texture maps, one to show the color of the surface, one to show which parts are metallic, and then one to show how rough or glossy the object is. And if you put them all together, you get a realistic light reflection. And of course, there's many shaders that don't use a PBR model, but are instead creating a stylized result, but we're going to focus on realism right now. If you've used Blender, and the Unreal material node will look familiar, or vice versa. There are inputs on both that are very similar. Unreal has a dedicated ambient occlusion input, and then in Blender, you need to mix the ambient occlusion with the color texture. But in Blender, most inputs have their little slider on there that allows you to quickly set an overall value, while Unreal requires a value node to be plugged in. But in most cases, if you've used one, the other one will look very familiar. And then, although we're not going to cover them here, the rendering engines of any node-based software will have nodes that are very similar to that. Okay, one more important thing before we look at each of the textures. The influence of a texture map will be on a 0 to 1 scale, and you can think of that as 0% to 100%. For example, if you have a light on a dimmer switch and it's all the way off at 0, then 0 light is being added to your room. If you push it up a little bit to 10% or 0.1, then you get a little bit of light. At 0.5 or 50%, halfway, half of the light's full power is on. At 100% or 1, you get the full effect of the light. And now look at the texture map over here in the corner. If this were a light map that was plugged into an emission channel, for example, then this diagonal white stripe would be glowing at full strength. But the 50% gray stripes on either side would be giving off half as much glow. And then the dark ones on the edges here, only a little bit of glow. And then the black corners would be 0% white or completely masking the effect. In other words, there would be no glow in those areas. You could also imagine that as like a window with paint on the glass, a backlit window. Areas of thin paint will allow a lot of light through, and the thicker the paint, the more light is masked and the darker the glass will appear. If I painted it completely opaquely black, then no light would be getting through this. So each one's a little different, but the 0 to 1 thing stays the same. All right, let's look at each one of these one at a time. So the easiest one to understand is base color. It's also known as diffused albedo or just plain old color. It's the simplest one to understand because it's basically just a picture of the image. You can think of it as a photo of the material. And this cube looks like it's wrapped in a photograph of cobblestones because we can see the surface color, but we can also see that it's totally flat and not reflecting any actual contours. Now there is a difference between color and albedo maps. A color map of a brick wall can simply be a photo of a surface, and in many cases that's just fine. But the shadows of the bricks are baked into this photo. And if you decided you wanted to light this wall with a torch sconce or something, or a bright light from below, then the shadows in the photo would look weird because they'd be kind of upside down. Whereas in the albedo map is just the color of the surface with no shadows or highlights. Albedo maps are harder to generate, but they're better in the long run, and they're able to work with any lighting conditions. But you can get away with, either one. Despite metal being an essential part of PBR workflow, we typically don't need a metal map unless there's parts of the object that are metallic and parts that aren't. Most surfaces are either all metal or all not. All not, the fancy word for that is dielectric. So stone, wood, plastic, dirt, concrete, etc. can just simply have their metal channel set to 0 metalness. If the thing is metal, then the channel should be set to 1. We only need a map if parts of the object are metal and other parts aren't. In this example, the map has a black circle in the middle of it, indicating that there is a non-metallic dot on each of the faces of the cube. So the white area there is 100% metallic, so we get this kind of like aluminum cube look with this like matte, flat, red dot painted kind of on the side there where the map has that circle of 100% black on there. So maybe it's like an aluminum box with like red painted circles. In any case, the white areas of the map are 100% metallic. There are a few instances where the metal value will be something other than 1 or 0, but they're very rare. Here you can see that the map at the left is being used to show a metal cube that's partially covered in rust. The black part of the mask is 0 metal, where the rust is, and the white part is 100% metal, where the chrome appears. Hopefully that can make sense. And then in Unreal, we can make a simple metal material very easily with just a few values. In this example, we could just put the color channel in with an RGB value of 70% red, 50% green, and 0% blue to make this kind of mustard yellow color. And then that color is plugged into the base color. And then we have a value node of 1, or 100%, plugged into the metal channel. And then just a little bit of roughness there, that 0.1%. 10% roughness there is just to keep it from looking too perfect. And with just those 5 numbers, we can make a simple but effective brass material. Okay, so roughness is a map showing where the surface is smooth and where it is rough. Some software uses glossiness, which is exactly the same thing but inverted. So white is 100% smooth instead of 100% rough. But Unreal, Blender, a lot of things you're going to encounter, or you can use that roughness map. In this map, you can see that there is a white circle indicating 100% rough and a black border that is 0% rough. And the middle is 50% gray, indicating that it's smooth but partially matte surface. And in the render, you can see that the cube is very glossy, reflecting the environment with a partially reflective ring and then a very flat circle in the center. So the reason that rough surfaces look rough is that all those little cracks and crevices break up the light and send the light bouncing off in all directions, so the surface looks matte. A smooth surface bounces all the light at right angles, making for sharper reflections. And that's also why wet surfaces look shiny, because the water gets in and fills in all those little cracks and crevices and then bounces back a smoother surface. We can also use roughness maps to suggest wear and tear and dirt and grime or whatever. Sometimes these are even called grime maps, just indicating. You can also imagine like taking some sandpaper to some glossy plastic. Wherever you sanded, you'd be adding a lot of little scratches that would be diffusing the light. So here in Unreal, we're just plugging in an RBG value in to get blue into the base color, and then using that same bullseye map from a few slides back, plugged into the roughness channel to suggest like a basic paint or plastic with 3 levels of glossiness. Now, roughness is a little weird to remember because it seems a little counterintuitive. You make the number bigger to get less reflections, so it's kind of a little backwards, but you can think of that as like a black car or a dark window is more reflective than a white car or a lit window, if you just need to kind of wrap your head around it. Now, specular is not really part of the PBR workflow, but it's important to know about. Specular maps are an artificial reflection where 100% white will give us a kind of a bright, shiny spot. But notice that in that little circle in the middle of our bullseye there, it's like really shiny looking, but there's nothing being reflected into it because it's not actually taking the environment into account. So you can kind of think about that as like an artist's drawing of a shiny object where they kind of paint in a little highlight to suggest the smooth surface, whereas an actual photo has the actual reflected environment in that surface. So that's kind of the difference between the specular and the glossiness or the roughness. Anisotropic is one of those things kind of fun to say. It's also known as a flow map. It's very rarely used except when you have to use it for these kind of surfaces. These are kind of the classic examples. Oh, like the underside of a pan, kind of brushed metal, hair, a CD-ROM, like I can't think of any other examples, So when you end up with these situations where you have parallel lines of reflectiveness, then you need that anisotropic map. It's very rarely used except when you absolutely need it. Normal maps, on the other hand, are one of the big ones. That's an important one. They are special in a lot of ways. So ultra-dense meshes like those that are being used in Unreal's Nanite may soon make normal maps less important for us, but for right now, they're essential to suggesting a lot of surface detail on a simple object. The cube here in this image only has 6 faces, 6 polygons on it, and all that detail that we see on there are the cobblestones, highlights, and shadows are coming from that normal map. So it's a way to kind of like fake surface detail, try to trick the lighting into giving highlights and shadows where there actually isn't any geometry. And the way that these are made, they're widely used in video games and visualizations to fake low relief or detail. Just imagine an object being lit with a red, blue, and a green light from 3 different sides. And then the computer is going to interpret those colors just to suggest the surface details on the object. The drawback of normal maps is that they aren't easy to make. There are tools that you can use to generate them, and they, sometimes it can be a little fussy. And you can also bake normal maps from a high poly mesh, but that's a lot of steps. But if you are downloading materials from a good material website, then the normal map will come with it. It's also important to note that there are 2 different types of normal maps, OpenGL and DirectX. It's usually easy to flip them, but if you use the wrong type, then your image is going to look inside out, concave instead of convex. So fortunately, Blender uses the OpenGL maps that are very common. Unreal is using the DirectX. So if you're using something from Blender into Unreal, you need to flip your map. But that's actually not very difficult. It's an easy fix. In Unreal, all you need to do is just double click on your image texture in the content browser, tick open the texture caret if you need to, and then find the flip green channel and check it. Or you can just search for the flip green channel. And don't forget to save it. Make sure that the compression is set to normal. Sometimes when it's inverted, it doesn't recognize it as a normal map. So you want to make sure that that compression setting says normal map. And then in this case, the OpenGL image that this creator made was nice enough to, the creator was nice enough to put the GL into the naming convention up there at the top. So you can actually see cobblestone floor 08 normal GL 4K. So like all the information is just right there in the name of the object. And that lets you know that if you want to use this in Unreal, you're going to need to flip it into the DirectX direction. All right, so let's get technical for one more time. This may actually make it easier in the future if you understand a few of these things now. There are 3 spaces. World space is like a compass. X, Y, and Z are going to point the same way regardless of the camera or the object's rotation, just like east and west are the same regardless of which way you are facing. Object space, on the other hand, is like right and left and up and down. Those are relative to the rotation of the object, just like left and right depend on which way you're facing, and the top of your head is the same whether you're standing up or lying down. Tangent space relates to each face of your object. There is a U and a V direction for each face, with the W, or the normal, projecting directly off of the surface. And then notice that the blue normal arrow is pointing directly off of the surface of the cube in 3 different directions, or 6 different directions if we could see all 6 sides of it. In Blender and Unreal, the red channel is used for X, Y is green, and Z is blue. Tangent space is important for normal maps as the light needs to react to the map regardless of the face's normal. So it's more easy to see this in the picture than it is to describe it. The highlights on each of the 3 faces are pointing upward toward the light that's pointing straight down, regardless of which way the face is pointing at. 99% of the time, this is what you want, and normal maps are in tangent space by default, so usually you don't have to worry about this. But if you start changing settings, weird things can happen. And not all software uses the same world space. Tools that have their origins in architectural or CAD software, like Unreal and 3ds Max and Blender, use the Z-up, with X and Y being width and depth, like in architecture, and Z is on the blue channel. Tools that have an animation DNA, like Maya and ZBrush, use Y-up. And the only time you really need to worry about this is if you're exporting a mesh from a Y-up software into a Z-up software, or the other way around, and your object will import on its side unless you specify that during your export. And even if you forget, it's just a couple of steps to fix it usually, but just be aware that it's not always universal depending on what software you're using. Okay, back to the rest of the easy stuff. A bump map is a simpler version of a normal map. It just uses a grayscale to fake the surface detail. They aren't as effective as normal or displacement maps, and they're best for small detail like rough stone on a stucco wall. 50% gray will be level with the surface, darker values will be concavities, and lighter values will be projections. And they're frequently used with the normal map creating the large detail and the bump map adding fine grain. All right, displacement maps are very powerful, but they're also very processor heavy. It's like the reason why, well, this looked great. Why don't we use them everywhere? It's because it's really going to slow down your renders. Similar to a normal and a bump map, a displacement map uses a grayscale value to actually offset the mesh. So instead of just faking it, it actually is changing the geometry. But you need a dense mesh with a lot of vertices and a high resolution 16-bit image to get good results. But unlike normal and bump maps that are only faking the surface detail, a displacement map is actually modeling it into actual 3D shape. And you can see that in this example that you can get a little tricky on sharp corners where the mesh is pushing away from the surface in 2 different directions, which is causing some weird stretching on the corners, but usually there's ways to work around that. A displacement map is moving vertices, but you need a dense mesh to get good results. A cube with 96 faces won't have enough verts to get good resolution, whereas a cube with 98,000 faces has a lot more vertices and then a lot more points to displace, or higher resolution is another way to think about it. With no subdivisions, a displacement map won't do much as the only verts are on the corners, so you'll just get this weird warped look. With 2 subdivisions, it'll start to work, but the result will look like dented metal. At 4 subdivisions, the bricks will start to appear, but they're still going to look pretty jagged. And for the bricks to look good, you need a lot more vertices. So unless you have a powerful computer, you want to avoid a lot of displacement, even though it does look fantastic. To use displacement in Unreal, there are several steps that are outlined on this slide. I'm not going to walk you through this slide right now. You can come back and just read this and follow along if you want to try it all on yourself, but I'm just going to show you this picture for now and then keep on going because we're almost done. Opacity is pretty straightforward. In Unreal, you need to set the blend mode of the material editor to translucent, and then all you need is a value or a map plugged into the opacity channel, 1 being solid, 0 being invisible. So in this example, 0.5 is like sort of like colored glass there. You can also use an opacity map, except that you need the texture to have an alpha channel. So PNG and those other ones there are what you need. You need that transparent alpha channel to actually make this work. So you can't use a JPEG. White is not the same thing as transparent. Opacity masks are used when you want part of an object or texture to be transparent. You need that alpha channel in your image to make it work. So you'll need a file like PNG that can save the alpha channel. Black is 0% opaque or solid, and 1 is fully transparent or invisible. But remember, we're talking about transparent, not white. Gray values on top of a transparent background will give you levels of translucency. In Unreal, change the blend mode to masked, and you might want to check that the two-sided box on there, in the example of our cube here, or else the inside of the cube will be invisible. Subsurface scattering is another one of those rarely used ones that looks really great when you need them, and that's just essential for effects where light is passing through an object like skin or wax or any kind of translucent materials. Subsurface materials in Unreal need to be set to the subsurface shading model. In this example, a 0.2 value is plugged into the opacity and a 3 vector is plugged into both the base color and the subsurface color, although you can, and in many cases you probably should, use 2 different colors. For the grape example on the previous slide, you could have a texture image of a grape skin going into the base color and then a pale green yellow into the subsurface color to get that kind of like the inside of the grape shining through. Animation is pretty straightforward as well. It's just a glowing material. In Blender's Cycle engine or in Unreal with Lumen turned on, emissive surfaces will actually give off light into the scene. In Eevee or in Unreal with Lumen turned off, a little bloom or some fog will fake the effects of the glow. In this example, if this is Unreal 5 using Lumen, emission can actually cast light into the scene. This glowing sphere in the image is the only light in the scene. Lumen's not only casting light, but it's also reflecting in the mirror, in Manny, in the glossy tiles back there. It's also bouncing light into the corners in a really realistic way. So it's a big step forward. You can use a mask, of course, with a emission shader. Here, a black and white mask is being used with a magenta color to make this glowing logo. So that kind of thing is pretty easy to do with a setup like this. And then ambient occlusion. It's a subtle effect, but it makes a difference when you're going for full realism. It's similar to a cavity map. It's just a grayscale image with darker areas suggesting cracks and crevices where not a lot of ambient light is bouncing around into the scene. So in a high poly mesh, there's usually enough geometry to get the job done, but an ambient occlusion map can really help define the edges of low poly scenes by darkening the corners. I mean, really, the difference between the on and the off down there, example with the lion in the foreground, that's really a big difference there. It looks really kind of washed out with the ambient occlusion off. So a lot of times you don't need it, but occasionally it can make a really big difference. And then it's not really a material, but decals are a thing that in Unreal, and you also find them in a lot of other software, images as planes or image props, or a lot of different tools have different names for them. But a decal is just basically a 2D image, oftentimes, although you don't have to have it, oftentimes with an alpha map that allows you to add a little detail like a sticker onto your surface. So like the drips down there on that wall, the clock there, just kind of stuck onto the surface. It's pretty easy to put them together. In Unreal, you'll need to change the material domain to defer decal and the blend mode to transparent if you're using an alpha map. If you're sticking a poster on the wall or something that's square, you don't actually need the alpha map or the translucent channel. channel, but in this case where we have invisible around the clock, we want that that turned on. And then just simply plug the RGB into the base color or the emissive color, and then the alpha channel, the A there, into opacity, and you're good to go. You might come across some weird looking textures with names like ORM or ARM. All this is a packed texture. And that means that especially with game engines, we really want to draw from the texture maps as few times as possible. Every time it's got to go look at a texture, it's slowing you down a little bit. And if you have hundreds of objects with thousands of textures in your scene, it's just going to drag. But one of the ways to get around that is to texture pack. Because if you've noticed, most of the textures that we're using are grayscale images. So you can get away with that with something like this texture here. This is the Unreal Starter Contents, the chair that you get at the default there. And it's using the red channel to hold the ambient occlusion, the green channel for roughness, and the blue for metal. So that ARM, that ARM, is ambient occlusion in the red, R for roughness in the green, and metal for blue. And you don't have to use that setup. That's the one that Unreal likes the best. Usually the green channel has more room, so you put the higher detail things like roughness into that green channel. But you can put them in any channel you want. You can also use the alpha channel as well. But then unpacking is very easy in Unreal because there's pins that you can just pull off and just remember, oh yeah, red is ambient occlusion, and green is roughness, and blue is metallic. I always think grass is green and rough, and blues and metal are both music, and then ambient occlusion is red. So, but anyway, in Blender you can still do this too, but you'll have to break it out into a couple of different more nodes. Anyway, but that's something that you might not run into for a while, but when you do, or you look at one of these, find one of these like weird yellow textures, like that's what that is. It's just a packed texture, and you can plug that in Unreal very easily. All right, so just a summary here to wrap up, it's all about light. So it would be a very odd material that would need all of these maps. In many cases, all you really need is a base color, roughness, and a normal map to get good results on a wide range of physical materials. And there's a few more like curvature and edge and radiosity, ID, parallax, things that are used by advanced texturing tools like Substance or Quixel. But if you understand the textures on this list, you'll have no problem with 95% of the materials that you will encounter. So if you kind of get these down, it's going to make building your materials in Unreal or in Blender or whatever a lot easier. So hopefully you found this useful.